So on the first question, how do we do that? No, that, the first question. So what you're suggesting, I want to do something with those exponents, right? And what is that? Divide by 2, so that turns into 3 squared times 2 cubed, which is 9 times 8, which is 72, right? All right. How about the next one? Difference of squares. But what should I do first? Right, flip around the plus sign, so write it as square root of 5 minus 4, square root of 5 plus 4, and then we see that's the difference of squares, right? So what is the square root of 5 squared? 5, and what is 4 squared? 16, so negative 11. Now what about the last one? Right, so I need to use our formula, so it's a square root of 2 squared plus the double product of that and that, so 2 times root 2 times 2 plus last squared. So if you compute that, square root of 2 squared is 2. 2 times 2, right? We get 4 square roots of 2, and then another 4, right? 2 plus 4. So that's that. Yay? Good. So that's our quiz. So now we're going to play more with these square roots. We're going to learn more of their properties. So new stuff. When computing square roots, like the best thing that I can ask you is something like, hey, what is the square root of 36? Because 36 is what we like to call a perfect square. Yeah, so the answer is 6. We don't have any problems with that. This is nice. We like that. Now, on the other end, if I ask you something like square root of 3, there's not much you can do about that. Square root of 3 is square root of 3. There's nothing you can do with that. But I can also ask you something like this. What is the square root, for example, of 27? Now, 27 is not a perfect square, right? Yeah. But the next best thing that I can do is to think of 27 as a product of a perfect square and something else. So can you think of 27 as a product of 9 and 3, right? 9 is a perfect square. So I can actually think of this as a square root of 9 times 3. And by the properties of the square roots, I can rewrite this as the square root of 9 times the square root of 3, which becomes 3 square roots of 3. So we can simplify radicals by extracting a perfect square out of them. Of course, you're not going to take that many steps. You're just going to say, well, 27 is 9 times 3, and the square root of 9 is 3. So this is really an unnecessary step right there. But do you see what just happened? Okay. Yeah, so then I'm thinking, okay, so two numbers, I can do square root of 9, that comes out as 3. But I cannot do square root of 3, so 3 stays under the radical. We do both. It's just I can take square root of 9, but I cannot take square root of 3. So that's why I keep the radical over the other 3, while the first 3 does not have it because it's already to the square root. Here's another one. How about square root of 32? 16 and 2. Now, in this one, you actually have options. You can do it 16 and 2, or you can do 4 and 8. But you always want to look for the largest perfect square. So 16 and 2 is the better option. So yeah, I can think of 32 as 16 times 2, and the square root of 16 is 4, and 2 stays under the radical, so it becomes 4 square roots of 2. Is that okay? Any questions on this? How would you do something square root of 50? 25 and 2. 50 is 25 times 2, and I can actually take square root of 25, so it becomes 5 square roots of 2. Okay? So what I can actually do with this, if I ask you a question like that, for example, square root of 32 plus square root of 50. These two square roots look very different, so I'm going to have problems adding these two radicals because they're very different. But if you actually perform this simplification first, square root of 32 becomes 4 square roots of 2, while square root of 50 becomes 5 square roots of 2. Yeah, because now it becomes just like combining like terms. You have 4 monkeys plus 5 monkeys. I'm just calling square root of 2 a monkey in this case. So that's 9, right? So just like combining like terms, 4x plus 5x, that's 9x. So 4 roots 2 plus 5 roots 2 is 9 square roots of 2. Right, just like that would be just like having 5x squared plus 4x. Those are not like terms. Okay. So a few more examples. How about something like this? If I have a square root of 81a, a is just a. Well, 81 is a perfect square to begin with, right? Yeah, so that whole thing becomes 9, but a stays under the radical. I know how to take square root of 81, but I have no idea how to take square root of a, so a stays under the square root. Does that make sense? So assume that a is greater than or equal to 0, so we don't run into any problems. So how about this example? If I ask you square root of 32a squared. So again, our job is to find perfect squares in that product. We already dealt with 32, right? We know that the best way to split 32 is 16 times 2. Now, a squared, to begin with, is a perfect square. But I can take square root of a squared. What would square root of a squared be? Hey, so I can take square root of 16, that's 4. I can take square root of a squared, that's a. But I cannot take square root of 2, so I will have that square root of 2 attached here. So it's 4a square roots of 2. How is that? Does that make sense? Now remember, in order for exponent to be a perfect square, it just has to be even, because I can divide it by 2. That's how we take square roots of exponents. For the coefficients, it really have to be a perfect square. Yes? All right, well, let's try something like that. How about this example? Square root of 9b to the 7th, a to the 5th type of thing. Okay? 9 is a perfect square. I don't have to mess with it. So I'm just going to keep it there. Well, b to the 7th is not, because it's an odd power. Okay? But just like with examples before, can I rewrite b to the power 7 as a product of a perfect square and something else? 4 and 3. But remember, I just need my exponent to be even. I don't need my exponent to be a perfect square. So what is the largest even exponent that's part of the 7? 1 and 6. I can split b to the 7th as b to the 6th times b. I can take square root of b to the 6th. I just have to divide the power by 2, right? How would we deal with a to the 5th power? A to the 4th times a, right? Because, again, I just need the power to be even. That makes it a perfect square. Now I can start taking square roots. Well, square root of 9 is 3, just like a numerical case. But what is the square root of b to the 6th? B to the 3rd, because I just have to divide the power by 2. And what is the square root of b to the 4th? I'm sorry, yeah, a to the 4th, a squared. And what stays under the square root? B and a. So that's it. So if you have an odd power, you can always borrow 1 to make the remainder even, and then you just take square root of that. Yeah? Let me do another one. Square root of 50 x to the power 8 y to the power 13. So again, the first step that I'm going to do, I'm going to split each component into products of a perfect square and something else. So we already dealt with 50. I'll split 50 into 25 and 2. Because 25 is a perfect square. Now, x to the power 8, do I have to mess with it? It's already a perfect square. Again, the exponents, all I just need for exponents is for them to be even. Well, how about y to the 13th power? I'll have to mess with that. How would you mess with that? Right. Y to the power 12 times y. All I need is an even power. Right? So then I can go ahead and take square root of 25. That's 5. I can take square root of x to the 8th. That is x to the 4th. Yeah, 2 stays there. And I can take square root of y to the 12th. That's y to the 6th. And under the square root, we still have 2 and y left. Is that okay? But that's just assuming that all variables are positive. Assume all variables are greater than or equal to 0. Because otherwise it gets a little technical when you start taking square roots where negative values are allowed. So how's this? Does that make sense? So with the numerical, you're literally looking for a perfect square. With exponents, you just need the exponent to be even. Any questions on that? Make sense? All right. So I just showed you that thing, but so adding square roots is just like combining like terms. So if I ask you, for example, to simplify something like 2 square roots of 3 plus 4 square roots of 3 minus 3 square roots of 3 minus the square root of 3, I'll just treat it just like combining like terms. I just need to combine all the coefficients. So I have 2 plus 4 minus 3 minus 1. So I have 2 square roots of 3 left. So that whole thing becomes 2 square roots of 3. So this is just like combining like terms. Okay, so the radicand has to be the same. If the radicands are equal, I can combine them. So this is just like going 2x plus 4x minus 3x minus x equals 2x. That's equivalent example. Do you see that? If I have something like this, 5 square roots of 2 minus 3 square roots of 5 plus 2 square roots of 2 plus 5 square roots of 5, I can combine square roots of 2 together. I can combine square roots of 5 together. But I cannot combine both of those because those are not like terms. So I can actually go 5 square roots of 2 plus 2 square roots of 2 that is 7 square roots of 2. And at the same time, negative 3 square roots of 5 plus 5 square roots of 5 will give me 2 square roots of 5. And that's all I can do. I won't be able to go any further. I cannot combine expressions that have different radicals. Is that okay? Here's another example. We already did something like that. Square root of 75 minus square root of 48. Those are not like, per se, right? Right, but I should at least try to simplify them. Maybe something will work out. So yes, you're right. 75 is 25 times 3. What about 48? 24 and 2, but those are not perfect squares. Remember, when you split the number, you want to, what? 16 and 3, because you want to have a perfect square. Right? So I can do square root of 25, that's 5, so that's 5 square roots of 3. And I can do square root of 16, that's 4. So it's 5 square roots of 3 minus 4 square roots of 3. Now, these are like terms. I can combine them into just one square root of 3. How's this? So does that make sense? We're just learning different tricks and operations we do on radicals. So any questions on that? You like that stuff? All right. Let me show you something else. So this is kind of moving forward with the radicals. So let's say you will be taking a class, a math class someday. So you're taking a math class and you do a complicated problem and you get an answer, and the answer came out, for example, 1 over square root of 2. So you did a lot of computation, you got that for an answer, and let's say that's a class where you actually have a book. So you flip in the back of the book to check your answer. Well, in the back of the book, it says that the answer is square root of 2 over 2. So you start freaking out, you're rechecking your work, and whatever, anything that you do, you get that. And the back of the book maintains that the answer is square root of 2 over 2. That happens sometimes, but very rarely. Because you know who writes the answers in the back of the book, right? Well, yes, the graduate student. That's who writes. Because usually a professor writes a book and then goes, here is $5 an hour, knock yourself out. Solve all those questions, put them in the back of the book. That's your graduate report. But anyways, but check this out. If I do this on a calculator, if I actually go 1 divided by the square root of 2, I get that 0.707-ish. Can you remember that? Okay. But if I go square root of 2 divided by 2, I get 0.707-ish. Right? So that's the same answer, numerically speaking. But this will happen a lot because we, at some point, we have decided that it's just grammatically improper to have a square root in the denominator. It's just almost politically incorrect to leave your answer in that form. So technically, although numerically you got the right answer, not so much. You will actually be marked off on the exam a little bit if you leave your answers with square roots in the denominator. Okay? So what we want to talk about now is this process, how to get rid of a radical in the denominator. And this process is called rationalizing the denominator. Actually, it's not hard at all. It's just an extra quick little step that we have to take that will help us out. So now think about this. What would get rid of that square root? What kills a square root? Square, right? So if I magically put a square next to the square root will go away. But that would be incorrect mathematically, because the only legal thing that I can do with a fraction is to multiply it by 1. I cannot just square that fraction, because if I square that, I'll get 1/2, which is not equal 0.707, right? So, but the way to square a square root is to multiply it by another square root. If I multiply square root of 2 by square root of 2, that's square root of 2 squared. Do you agree with that? Well, if I multiply denominator by the square root of 2, I will have to multiply the numerator by the square root of 2. So now I'm consistent with my legal steps on fractions. I'm multiplying it by 1, which is always okay. Now what happens, you multiply fractions straight across, you end up with the square root of 2 over the square root of 2 squared. Literally, right? Square root of 2 times square root of 2 is square root of 2 squared. And that kills the square root in the denominator, and you end up with square root of 2 over 2. Yeah. And one of the biggest reasons, I mean, except for being, politically correct and grammatically accurate, God forbid you're going to be asked to add fractions that have radicals in the denominator. So finding the common denominator would be a nightmare. But if you turn your denominators into integers like that, then adding fractions will become a lot easier. Finding the common denominator will be easier. Does that make sense? That's really the reason. Because if you start adding those types of expressions, having integers in the denominator makes finding the LCD a lot simpler. Okay? Here's another example. So 3 over square root of 11, so it has a radical in the denominator. How do we get rid of that radical? What do I have to multiply that by? Yeah. Multiply by square root of 11 over square root of 11. So that's 3 square roots of 11 over, this is square root of 11 squared. So then it just becomes 11 in the denominator. Is that okay? And that's it. If you have a single square root, it's pretty straightforward. You just multiply it by itself. Now, here's another example. How about 5 over the square root of 32? Yeah, but in this case, I can simplify the square root of 32. We'll make it again, we'll make a smaller fraction. If you simplify your square roots first, we've dealt with the square root of 32 today. We know that square root of 32 is 4 square roots of 2, right? Now, the square root of 2 is the only troublemaker. 4 is okay. I don't have to fix 4. 4 is an integer. I just need to get rid of the square root of 2, so I need to multiply this whole thing by what? Yeah, just multiply by the square root of 2 over square root of 2. So if I do that, it comes out to be 5 square roots of 2 over 4 times square root of 2 squared, like that, if I actually write that extra step. Right, you just multiply straight across. So what is the square root of 2 squared? 2. So my denominator is 4 times 2, right? So it's 5 square roots of 2 over 4 times 2, so which is 8. So it's 5 root 2 over 8. How's that? Is that okay? Does that make you happy? It's not that bad, right? If you have a single square root, multiply it by itself, it gets a little bit naughty if I have something like, well, let me try a different example. How about if I have something like that? So it's 3 divided by 5 minus square root of 3. So that has a square root in the denominator. Well, how? Don't write this down. Let me show you what happens. If you multiply it by that, you'll end up with 3 square roots of 3 on the top. But on the bottom, you'll end up with 5 square roots of 3 minus 3. So you still have a radical. So that doesn't work. Well, let's try that. If I multiply by the whole denominator, so that's 5 minus square root of 3 over 5 minus square root of 3. So that becomes 3 times 5 minus square root of 3 over 5 minus square root of 3 squared. Right? Will that get rid of the radical? Because I have to use the formula. If it was the other way around, if I had only a single number in the denominator, then I can do that. But when it's 2 in the denominator, it doesn't separate like that. So just based on your quiz today, you've seen that if you actually go ahead and perform 5 minus square root of 3 squared, that's 25 minus the double product, so that's 10 root 3 plus the last square. So actually end up with 28 minus 10 square roots of 3. That's what happens if you just square that. It still has a radical in it, right? So that doesn't work. But what does? What is that thing I've been showing you earlier and keep stressing? That there's a way to take a number that's irrational and multiply by something that always comes out to be an integer. And we actually gave it a fancy name that starts with a C. Conjugate. If I multiply by same expression only with an opposite sign, then I'll be using a difference of squares formula, and that will come out to be an integer. If I flip back to your quiz, look at the last example. Just simply squaring a number like that does not get rid of the square root. But the one before, when multiplying two conjugates, will always come out to be an integer, right? So when you have an expression that has two terms, one of which is a radical, then the only way to get rid of that is to use the conjugate trick, is to actually multiply by 5 plus square root of 3 over 5 plus square root of 3. So this will utilize the difference of squares formula, and it will get rid of the square root in the denominator. So that's 5 plus square root of 3 over, so this product is just difference of squares, so that's 5 squared minus the square root of 3 squared, right? Difference of squares. So this becomes 3 times 5 plus square root of 3 over 25 minus 3, right? So 3, 5 plus square root of 3 over 22. And you can leave it like that. Your denominator now is an integer. So when you have two terms in the denominator, if at least one of them is a square root, then we'll have to use a conjugate trick to get rid of that square. That's how you rationalize the denominator in that case. So let me do another one. 1 over square root of 3 minus the square root of 2. So what should we multiply that by to get rid of the square roots? Yeah, just go for the conjugate. It's okay if there are two radicals. The conjugate trick will get rid of them. So multiply by the same expression, only with a positive sign. And that will utilize the difference of squares formula. Then in the numerator is just times 1, so that's square root of 3 plus square root of 2. While in the denominator, it is square root of 3 squared minus square root of 2 squared. Yeah? Which is just 3 minus 2. Which is 1. So this is square root of 3 plus square root of 2 over 1, which is just square root of 3 plus square root of 2. Right, so you would just go for the opposite sign. That's what a conjugate is. So, and the reason for that, if you have opposite signs, then difference of squares formula kicks in, which will square each term individually. And that's what you want, to get rid of those square roots without creating anything extra. How's that? Now, again, this really kicks in if I do this example. If I try this to, to simplify something like that, 7 over square roots of 7 minus 2 over square root of 7 minus square root of 5 plus 4 over square root of 5 plus square root of 3. I have this expression. Well, that's a, some difference of 3 fractions, and as you know, in order to add or subtract fractions, you need to find the common denominator. Now, these 3 denominators are extremely different from each other. Where? The last one? That's 3. So technically, the LCD for these 3 fractions as it's written is square root of 7 times square root of 7 minus square root of 5 times square root of 5 plus square root of 3. That's the LCD, and it's just nasty. Okay? And I'll have to multiply the numerators by whatever is missing. I'm going to get a big mess of those square roots. So this is why rationalizing the denominator first will make her life a lot easier. If I rationalize each one of those fractions to make my denominators just integers, finding the LCD will be a lot easier. You see what I mean? So this is the real reason why we do that. Rationalize the denominator. So first, we would rationalize each denominator. So I'm just going to take them individually, one by one. 7 over square roots of 7. That shouldn't be too bad, right? We like when it's just a single square root. What do I have to do in order to rationalize that? What do I have to multiply this by? Yeah, root 7 over root 7. So multiply by itself. So if I do that, it comes out to be 7 square roots of 7 over square root of 7 squared, which makes it 7. So 7 square roots of 7 over 7. Right? I know. No, it's okay. You can totally do this in your head. So 7's cancel, square roots of 7. What? Is that okay? So the first expression just turned into square root of 7. Now let's take a look at the next one. 2 over square root of 7 minus square root of 5. How would we do that one? What do I need to multiply that by? Right, square root of 7 plus square root of 5. Because then I can use the difference of squares formula. So that's 2 times square root of 7 plus square root of 5 over, using the difference of squares formula, it is square root of 7 squared minus square root of 5 squared. Right? Which is 7 minus 5. Right, this is just 7 minus 5. So that's 2 square root of 7 plus square root of 5 over 2. So I can cancel those 2's, and we're left with square root of 7 plus square root of 5. No denominator canceled. Is that all right? How we got that? And the last one is 4 over square root of 5 plus square root of 3. So what do I have to multiply this by to get rid of the square roots? Square root of 5 minus square root of 3. So always go for the opposite sign. So that gets rid of the square root. So that becomes 4 times square root of 5 minus square root of 3 over square root of 5 squared minus square root of 3 squared. Is that okay? Which is 5 minus 3. That just 5 minus 3, so that equals 2. So 4 times square root of 5 minus square root of 3 over 2. And I can reduce 2 into 4. 4 turns into 2, so that's just 2 square root of 5 minus square root of 2. Minus square root of 3, sorry. So we got really lucky with this problem, right? Because there are no denominators at all now. So that's not just easier for having integer denominators. I mean, that's different level of being easier. No denominators at all. So this whole problem, remember what that problem was. It was the first expression. So the first expression turned into the square root of 7, right? Minus the second expression, right? Minus the second. Now the second turned into a sum of root 7 plus root 5, right? Now I have to be very careful because I have to subtract that entire expression. So I want to put parentheses around it. So root 7 plus root 5 like that. That makes sure that I'm actually subtracting the entire thing. And then plus whatever's left out of the third expression, which is 2 times square root of 5 minus square root of 3. Isn't that a lot easier to deal with? So I just open up parentheses, combine like terms, square root of 7 minus square root of 7 minus square root of 5 plus 2 square roots of 5 minus 2 square roots of 3. 7's cancel. Negative square root of 5 plus 2 square roots of 5 is just square root of 5 minus 2 square roots of 3. So a lot easier. Well, I had 2 square root of 5, but then minus square root of 5. So that combined into just 1 square root of 5. Right? I'm just combining like terms. So these two. So it's minus 1 plus 2 still leaves you with 1. Okay, so this is really the reason why we rationalize the denominators. Because again, to just perform this operation when denominators are like that, it's hellish. It's going to be very hard to do. But if you just rationalize them individually, I mean, that's really the best case scenario when all denominators just canceled out. It doesn't happen every time. But if they didn't, oh well. You can find the LCD if it's just integers. It's easier. Okay, good. Well, that's all I had to show you today. Now you're going to play with the worksheet. It's a little shorter than the last